back to general chemistry. We'll talk a little bit about atoms and compounds in this chapter. We've talked already a little bit in class about the difference between philosophy and science. Plato and Aristotle taught that matter was continuously dividable. For example, we could take a piece of gold, and if we had a sharp enough knife and good enough muscle control or machine control, we could continue to divide that piece until it got microscopic and smaller than microscopic, and no matter how far we divided it, if we had good enough control, we could continue to divide and still have gold. Democritus, who lived around the same time, taught that at some point you would get to the smallest possible piece of gold. The Greek word for indivisible is atomos, so he called that an atom. But Plato and Aristotle were better arguers, better debaters than Democritus, and he lost the argument. At least for that time period. About 2200 years later, John Dalton made some discoveries that actually proved Democritus was right. One of the things that Antoine Lavoisier noticed is that when he carefully measured his reactants and his products and made sure nothing was lost and nothing was picked up, the amount of reactant and the amount of product was the same, that no mass was created or destroyed in chemical reactions. Scientist named Proust made the discovery that different samples of pure chemical compounds always contain the same proportion of the elements by mass. So he found that water, for example, if we separated it in hydrogen and oxygen, would have 8 times as much mass of oxygen as it does hydrogen. It's because even though there's twice as many hydrogen atoms as oxygen in water, oxygen are much heavier atoms. And then a little bit later, the law of multiple proportions, the idea that some elements can combine in different ways to form different chemical compounds, and the ratios, if we compare one compound to another, are small whole number multiples of each other. For example, nitrogen and oxygen can form several different compounds, N2O, N2O3, so there'd be 3 times as much oxygen compared to nitrogen on N2O3 as N2O. A chemical compound, then, is a pure substance that's made of 2 or more elements that are joined together in a specific ratio. The chemical formula for a compound is symbols and numbers that indicate the ratio of the elements in that compound, and a chemical equation describes a chemical reaction by listing the reactants' formulas on the left side of the arrow and the products on the right. John Dalton, 1803, because of several experiments that he conducted, came to the conclusion that elements are made up of tiny particles called atoms. He considered those to be indivisible. He didn't know yet about electrons and protons and neutrons. So he thought that each element was characterized by the mass of its atoms. So that's something that's been improved upon since 1803. Elements are characterized now more accurately and more precisely by the number of protons that they have. So that's a slight difference between current atomic theory and Dalton's. The chemical combination of elements to make different chemical compounds occurs when atoms join in small whole number ratios, and that's why we have the law of definite proportions and the law of multiple proportions. So this was Dalton's explanation for those laws. Chemical reactions only rearrange how atoms are combined or attached or not attached to one another in compounds. The atoms themselves are not changed. Now, you get later into the 1800s, and scientists starting to think more and more about what electricity is, and they realized, J.J. Thomson in particular, British scientists, realized that electrons traveling through cathode ray tubes exist because they come out of atoms, that electrons can be taken out of atoms, and what's left behind is a positively charged ion. And so he started to work out a slightly different model for the atom, where the atom was visualized as being kind of a plum pudding, and you can see some pictures in the book that will help with understanding this. The atom is viewed as being having the positive charge spread throughout a pudding, and the negative charge should be able to be plucked out as plums. And that's not the most accurate view that we have of the atom today, but it was the best that had been done by the late 1800s. As he did his measurements and his experiments, he was not able to calculate the mass of an electron or the charge, but he was able to do experiments that gave the ratio of the mass to the charge. So it's kind of like being able to know the density of a metal, but not knowing the particular size or mass of a particular piece. He knew the charge density, the charge per mass, or the mass per charge of an electron. Robert Millikan did an experiment, I'm going to show the picture on the next page, that was able to calculate the charge on an electron, and therefore able to use Thomson's method, Thomson's work, to calculate the mass. The way that worked is he took some oil and sprayed it in a very fine mist into this box, where he had a telescope that he could watch what the oil droplets were doing. They dropped through a pinhole in this plate, and this plate has a positive charge that is controlled, how positive it is and how negative this one is, from a controller that he had outside the box. As the droplets drop through the pinhole, they get hit with X-rays, and the X-rays knock some electrons loose and cause some then of the oil droplets to be negatively charged and some to be positively charged. It causes an electron transfer. When that happens, those droplets are repelled by this plate and attracted by this one. And so what Millikan found is that he could suspend the drops in midair and get them to stop moving, where he could watch them sitting still right here. And he was able to do that with particular charges on the plates and not others. And he noticed that the charge on the plates needed to be a certain whole number multiple of an individual number. In other words, there was a unit of charge that every total charge on the droplet was a multiple of. So that must be the smallest unit of charge. That must be the charge of an electron. And so from that he was able to use Thomson's numbers to calculate the charge on, to calculate the mass of an electron, and we still use those numbers that they calculated today. Now Ernest Rutherford, early 1900s, believed Thomson's model of the model and wanted Thomson's model of the atom, and wanted to confirm those ideas by running an experiment of his own. And so gold is one of the most metallic metals there are, and the property that it has that's very, very metallic is that it can be hammered out into a very, very, very thin sheet without breaking it. So he takes a very thin piece of gold foil and he makes a radioactivity gun. Radioactivity gun, all you need is a radioactive sample like uranium or radium that gives off alpha particles. And you put it in a lead box where the radioactivity is only able to escape through one small pipe. And so the radioactivity comes out in a very straight line. Zinc sulfide lights up when it gets hit with charged particles that come from radioactive items. So he surrounds his gold foil with a zinc sulfide screen. And his expectation, if Joseph Thomson was right about the model of the atom, was that all of the radioactivity would go straight through this very thin gold foil and hit right back here, and we'd have no lights anywhere else. But what we find is that some of those radioactivity bits are deflected, and some of them are even reflected, bounced back, and that surprised Rutherford quite a bit. He had to completely revise the idea of how an atom was shaped, and what an atom's nature was. And he said if a very small number are being reflected, then there must be a very small area of the atom that is very, very dense. And so we got this idea that all the positive charge and most of the mass of the atom exists in a very small area, and the alpha particles, the radioactivity that was deflected, were the ones that were grazing that small area that we now call the nucleus. And the ones that got reflected were the ones that were direct hits on the nucleus. And so we got this idea that maybe an atom is something like a solar system, and the nucleus is behaving like a star or a sun, and the electrons are behaving like planets revolving around it. And that was the dominating atomic theory for the next 15 years or so. It's still not the best model we have today, but it was the best model in its day because it explained all previous experiments, including Ernest Rutherford's. Now, what we know about the nucleus today is that the atomic number, we give that the letter Z, is the number of protons that are there in the nucleus, the number of positively charged particles. They are about 2,000, almost 2,000 times as heavy as an electron, but they have the same amount of charge as an electron. It's the opposite charge, so we call it positive, and we call the electron's charge negative, but it's the same amount of charge, just opposite direction. In the nucleus are also neutrons, and they have about the same mass, not exactly, but close to the same mass as a proton. So the sum of the numbers of protons and neutrons in the nucleus we call the mass number. We don't include the electrons in the mass number because their mass is very, very small compared to the mass of the proton or the neutron. And so what Dalton didn't understand, what Dalton didn't have the equipment to find out in 1803 was that sometimes we can have an element that has two or more different masses. It's the same element. For example, carbon has 6 protons, and it has 6 protons and is carbon whether it has 6 neutrons, 7 neutrons, or 8 neutrons, and all 3 versions of those exist in nature. And so carbon-14, from a mass perspective, has 6 protons and 8 neutrons. From a mass perspective, it looks just like nitrogen, because most nitrogen atoms have 7 protons and 7 neutrons. Mass is 14. And it has a lot closer mass to nitrogen-14 than it does to carbon-12. But its behavior chemically is the same as carbon-12. So what we're going to do, I want you to take a look at the book and see how they show isotope symbols in the section on isotope symbols, and or you can Google it. And we're going to practice some of these isotope symbol writing in class. Now, an atomic mass unit is, as it turns out, it's the mass that we're going to assign to be 1/12 the mass of a carbon-12 atom. So it's approximately the mass of a neutron or of a proton, somewhere in between those. And the atomic mass then for an element is going to be the average of the mass of all the isotopes. Most, if you look at a periodic table, you'll see carbon's mass is 12.011. That's because about 99% of the carbon that exists in nature is carbon-12, and about 1% is carbon-13, and a much, much smaller percentage than 1% is carbon-14. The number of atomic mass units that are in a gram, the number of carbon-12 atoms that would have to be assembled to get 12 grams, is 6.022141 times 10 to the 23rd. I expect you to memorize the first 4 significant figures of that. So 6.022 times 10 to the 23rd is the number of atoms in what we're going to call a mole. It's how many atoms or molecules we have to have for our mass in grams to be equal to what's written on the periodic table. Alright, so the video is about to end here. I want you to pause it before it ends. Write this problem down. This is one that we're going to work together on in class, but I'd like you to do the best that you can to work this problem on your own before we meet in class next time. So that means next time we're going to look at isotope symbols and how to write them, and then we're going to look at isotope abundance. And this is a problem that's worked in the book. It's example 2.5 if you want a little bit of a hint on how to do it. We'll finish up the chapter 2 in a second video that'll be posted in a little while.